Good morning, everybody. Last day. I'm glad to see actually pretty good turnout. For the last day of a conference, I'll take it. So, okay. I am here to talk about doesn't matter what AP you buy in 2025. So I'm Wes Purvis. I do wireless things. And this talk sounds familiar. You may remember because it does actually sound familiar. I gave a talk with a same title in 2018. So 7 years ago. And so the idea behind this session is this still relevant, right? You know, there's a lot that's changed over the years. And so, from a Wi-Fi perspective, does it actually matter what you buy? This isn't like which vendor go buy. This is a technology presentation on, different AP models, technology, and other considerations. So let's think about what's changed. Personally, I've moved twice. I think Troy moved out of Prince Albert, and our music choices have changed as well. Time goes on, I guess. So from a Wi-Fi perspective, there's been quite a lot of things that have changed. We have basically the death of 3x3 from a client and AP perspective. We've gone through 3 generations. At the time of my last presentation in 2018, Wi-Fi 5 was in its prime. That's 11AC Wave 2. We did not yet have the 6 gigahertz band. I think we were still surveying with dongles. A lot has happened. Who remembers this guy, the Intel 6300? This was released in 2011, but this was the client. 7265, 8265 were just kind of coming out, but this was a 3-stream 11N client. The MacBooks at the time were 3 spatial streams, right? The 11AC MacBooks that were released in 2013 and didn't really get refreshed until the Apple Silicon Mac. So 3 spatial streams was kind of the was state of the art, let's say, and folks were just kind of starting to do 4x4 in 11AC Wave 2, and so the combination or the major focus of my talk last time was 3x3 versus 4x4. Since 3x3 doesn't really exist anymore, I'm going to focus on 2x2 versus 4x4. So here's kind of just a comparison again, 2018, 2025. So most of the APs, on the low end were 2x2 and 3x3, and then you had some 4x4 coming out. From a client's perspective, you had a decent amount of 1x1, a much higher concentration of even 11G or 11A, 11B, whatever it is, and then the 11N capable clients and higher 1x1, 2x2, and 3x3. You actually had 3x3 clients. Your peak data rates for a 2 spatial stream client on 20 megahertz was 173 megabits per second. That was two spatial streams, M9, right? And at the time, that's 256 QAM. 256 QAM was sort of hard to achieve in the kind of the first generations of 11AC. If you had an 80 megahertz channel, which you probably did not, but you could get up to 867. So for all practical purposes, the maximum data rate you would see was 867 megabits per second. Now in 2025, we have Wi-Fi 7. The APs have settled on 2x2, 4x4, maybe a mixture of both of those, depending on the radios. Almost all clients have settled on 2x2. You still have some 1x1, but those are generally by exception. And most, not all, of our BGA has disappeared. Who still has a healthy collection of 11B clients? I'm sorry. How about 11A or G? Okay. Who still has a healthy population of 11N clients? Okay, we'll get some more hands coming up. And how about healthy collection of 11 AC clients? Okay. Kind of what we see in most of our customers is about a 60% 11AX, 70% 11AX, 30% mostly 11AC, but the spattering of everything else. So we've come a long way. Our data rates have also improved, right? So if you compare again, like for like on 20 megahertz, just looking at the same modulation coding scheme, right? A 256 QAM, 11 BE rate, that data rate is 195 megabits per second for the same 256 QAM, right? So we've actually, we've gotten more efficient, we've gotten better at transmitting. If you go up to M13, 4K QAM, your data rate is double, nearly double, right? 341 megabits per second. If you go to 80 megahertz channels, which with 6 gigahertz is actually practical in some areas to deploy 80 megahertz, your data rate for a like for like, right, 256 QAM data rate is 961 versus 867 megabits per second. And if you go to M13, you're at 1.4 gigabits per second. So you have with these newer clients, you have the ability to have better data rates. And so this is just to show, we've gotten more efficient. The standards have advanced, and so have some of the clients. Now, this data is not strictly relevant to this presentation, but it's sort of relevant to the last slide, so I wanted to show it anyway because I had it. So this is the looking at missed customers on across our cloud. These are the percentages of channel widths in use across our APs. So on 5 gigahertz, we're predominantly 20 megahertz. So about 60% of our customers are using 20 megahertz channels, or I should say 60% of our APs are on 20 megahertz channels. Our default channel width in 5 gigahertz is 40 megahertz. And so I think there's actually an inherent bias to 40 megahertz, but that's still only 40% of our channels. Almost nobody is using 80 megahertz, so very happy with that in 5 gigahertz. In 6 gigahertz, it's a slightly different story. And I've actually broken it down between worldwide and Europe specific because we see a difference. This difference doesn't exist in 5 gig. So if I look worldwide at our APs, in 80 megahertz, we're 60%, over 60% are using 80 megahertz on 6 gig. But if I compare that to Europe, that number drops to 40, about 40%. That's because in Europe, most of our customers have elected to use, or many of our customers have elected to use 40 megahertz, which is also good. So in 6 gig, our default channel width is 80. So again, there will be a bias towards 80. But I just thought this was interesting data. It kind of relates to the practical data rates that you can actually achieve, and the increases in throughput that you may expect that come along with that. One of the easiest ways to increase your throughput is to increase your channel bandwidth. Now, of course, that assumes you have the channel reuse and the availability. So, this shows that it's actually doable to use wider channels in certain environments. So let's get to what I really want to talk about, which is looking at 2x2 APs and 4x4 APs. Is there actually a difference? Does it matter? Why do we have 4x4? Right? It costs more money, but does it actually kind of get you anything? So a little recap or primer. So here's a radio board. There's actually 3 radios on here. I'm only going to talk about 2 of them. So on that left side that's a 2x2 radio. It has 2 antenna chains coming out of it. Those could be transmitters, receivers, transceivers. You have a second radio that has 4 antenna ports connected to it. So when you say 2x2 or 4x4, there's actually 4 antenna leads coming out of the access point or coming out of the radio. You would have 4 physical antenna elements, each connecting to one of these. So on the left, that's 2x2. On the right, that is 4x4. Now, in some cases, not all of these could transmit, not all of these will receive. And that's most common, I think, in most of our APs these days. You have symmetrical transmit receive, but it's possible that you could see, like let's say 3x4 or 4x3, where one chain isn't transmitting or one chain isn't receiving. Let's also talk about the concept of MIMO gain. So the reason that we have multiple transmit chains on an access point is because of MIMO, multiple input, multiple output. And those multiple antennas that are shown here, right? Those are all individually transmitting. Now they work as a system, but if you look at antenna polar plots, depending on which plot you're looking at or who's providing it, you may see this level of detail, which is each line on here actually represents an individual antenna element. And then most common is you will also see an extra line, which is a composite line. That is the combination, including the MIMO gain, of each element. And so you may actually see antenna elements that have a kind of a null, but if you take the average of the composite, it'll look kind of filled in. And so this is just to say, when you take into consideration all of the antenna elements, you will see some form of antenna gain where you can combine your transmit power. And the way that you combine that is with the logarithmic equation. So the function is to get to the total power out, you take the individual per path transmit power, and then you add that to 10 times the log of the number of antennas that you have. So for example, if I am transmitting at 10 dBm per path on a 2x2 AP, I would take 10 log 2, which is about 3. So 10 plus 3 equals 13 dBm of total power. On a 4x4 AP, 10 log 4 is about 6. So 10 plus 6 is 16 dBm. So you would typically expect to see about a 3 dB delta between a 2x2 and a 4x4 AP in the transmit direction. And that's because of your MIMO gain. Now, most APs will, or most infrastructure systems will compensate, for the 2x2 AP, because then your neighboring APs don't hear as well, so you need to boost the 2x2 AP. Now let's look at, does the theory match reality? So this is a very simple test. This was a MacBook client, and taking the same access point, just in software, changing from 4x4 to 2x2. So on the left side is 4x4. The average RSSI there was negative 52 dBm, and then you have the big spike when the radio changed and the client had to reconnect. And then after that, when the access point was in 2x2 mode, the received signal strength on the MacBook was negative 57. So that's 5 dB. That's more than the 3 dB in theory, but we live in an imperfect world, and that the world tends to get in the way. So if the math says it's 3, it could be 0, it could be 6, it could be, it just kind of averages out. It should average out to about 3 or 4. So this is a good validation that, in general, the theory matches reality, and there is actually, this concept of MIMO gain. It exists in the real world when you have multipath. Right? Without multipath, your MIMO gain, it's much more difficult to take advantage of the multiple spatial streams. So let's take this one step further, and this is the kind of data I could not gather last time, so I'm super happy I can. This is a composite, again, looking across the MIST universe of 2x2 APs versus 4x4 APs in the transmit direction. So on the y-axis, that's data rates. On the x-axis, that's RSSI. The RSSI is not, it's how the AP hears the client. It's just, I have it on this plot even though it's receive RSSI so that we have buckets. We can see data rates versus RSSI. And so at first glance, it kind of looks similar, right? The bright green and the yellow, that's that's where there's more data. That's where there's the majority of data rates that are in use by the access point. So, but if you kind of, let me put a little box around these. So on the left, on the 2x2, the majority, the hottest spot is sort of in the middle there, right? Around the 400 megabits per second and about negative 60 dBm for signal strength. On 4x4, it's up and to the right. So there is actually the data rates that are in use from a 2x2 AP versus a 4x4 AP across, on average, right, across a large data set is higher. Again, good. From an AP vendor perspective, that's really good to see. So this was a kind of matches to our expectation. On the receive side, the story is about the same. Now there's a little data anomaly here, so things are. You'll actually see us, that line on the bottom. But if we again taking a look on average, again it's the comparison between the 2x2 and the 4x4 is in the middle and then up and shifted to the right. So it's about a 100 to 150 megabit per second PHY rate, right? These are the PHY rates difference between 2x2 and 4x4 on both transmit and receive. And then it's about we see about a 4 to 6 dB difference of how the APs can hear the clients. And that's all because of MRC. So we see advantage for 4x4 and 2x2. We see advantage for 4x4 in across our data sets, which again, good to see. The question is, does it matter? Like, does it actually mean anything? So one more metric to look at is the retry rate. So the red lines here are 2x2, the blue lines are 4x4. The one with the up triangle is for receive, and the one with the down, or the V, is TX. So it's sort of, everything's sort of together, but if you look kind of here, so let's compare the down triangle to down triangle. There is actually quite a bit of difference, especially at weaker signal strength. And then as you get to sort of the neg 60 to neg 70 range, it kind of equals out. And then actually when we get below neg 60, we're a couple percentage points higher in terms of retries on the transmit direction for 2x2. And then if I look at the receive side, again, it's about a 3 to 4 percentage difference. So we do actually notice in addition to the data rates that are in use, a lower retry rate with 4x4 APs. Let's add in some throughput, because does this signal, does the PHY rate, does the retries, does the signal strength, does it actually equate to anything? So here is multi-client throughput, actually using multiple vendors. The vendor A and the vendor C here do not necessarily equate to A and C. I'll just put that out there. I promise. So this is with a 4x4 AP and a 2x2 AP, and in general there's a 10 to 20% difference bidirectional throughput between the 2x2 and 4x4. Now this, it's hard to exactly attribute this specifically to RF. It could be the APs, on the 2x2 side could be a lower end generation. But in general, versus when you compare the 2x2 to the 4x4 AP, you will see or should expect to see some differences in throughput, which matches up with the differences in the signal strength and PHY rates and retries. Let's talk about the tiers of APs, or product families. So in general, most vendors have a good, better, best, or good, gooder, better, betterer. There's multiple APs, and those multiple APs you'll see 2x2, you'll see 4x4. You'll also see a bunch of different other features that the access points might have. And so some of those features, maybe on the higher end APs, you have better, more capable radios, discrete radios versus an SoC. You have a better front end with better quality power amplifiers, or the front end modules may be better. Those themselves can, all things equal, will make a tremendous difference on the quality of how well you're actually able to transmit and receive, which will improve your data rates. You may have flexible radios where the access point is capable of software configuration of one or more radios on the higher end APs. More memory, more CPU for handling and queuing traffic, or performing other tasks like deep packet inspection or other analytics that seem to, we went from the fat AP to the thin AP, and we're sort of like, growing again, from the AP. So faster Ethernet, a gig, multi-gig, almost every enterprise access point these days has a multi-gigabit. Some have multiple multi-gigabit ports. You may see redundancy capabilities on the access point. And then sort of, on the higher end, more bells and whistles are being added for like non-Wi-Fi capabilities, like location, sensors, IoT radios for handling of various use cases, GPS for standard power, and possibly other uses. So it's not just the RF where you see the differences in these AP tiers. It's the capabilities of the AP in general. The other thing to think about is, I need to deploy an AP for my particular use case. And so you may need an access point with external antennas to get a very specific pattern. Here's a warehouse-style antenna deployed in a warehouse, high racking, and it has a very nice long and narrow pattern that works well for kind of down an aisle. You may also see access points with a built-in directional antenna. And so the majority of access points deployed today, omnidirectional, right? Because it's easy, you don't have to really think a lot about it, and it's pretty safe. But as the density of access points increases, using a directional antenna in environments where you historically would not use a directional antenna, such as in like a corporate enterprise or a school or university classroom, where it's been either cost prohibitive to buy an external antenna, or just a pain, right? That's where the kind of this concept of a directional antenna built into the access point for more day-to-day use, could come in. You may also see access points with the flexible radio, like I said, and I want to spend a minute talking about those. And so over the years, there's been many flavors of multiple of the flexible radios, and by and large, as an industry, we've sort of settled on this concept of a high and a low AP or radio when you're in the dual 5 or dual 6 mode, where let's say you're in dual 5, one of the radios will operate on the low 5 gig channel, so that's Uni 1 and Uni 2, channels 36 through 64, and then the other radio will be the high radio, which is 100 through 165. Same concept on 6 gig, although this is pretty new for most people. And it's interesting to think about so let's talk about dual 5 first. With the high-low concept, it comes with one drawback, which is on the low side, you only have 8 channels, right? 36 through 64, that's 8 channels. On the high side, I could have 17, or if I add in Uni 4, that's 20 channels on the high side. And so if you're doing dual 5 gigahertz everywhere with this kind of model, you'll run into channel reuse issues, right? You essentially have 8 non-overlapping channels. On dual 6, where the split is Uni 5 with a break with Uni 6, and then Uni 7, 8 is the high side, you actually have a much more even distribution of channels. So just one consideration, if you're deploying dual 5, you may want to think about using it sparingly, or where it makes most sense, because you could possibly run into channel reuse issues. And just kind of simply, friends don't let friends do dual 5 with 40 megahertz channels, because then you go down to 4 non-overlapping channels. And my last slide, which is the other stuff on the APs. There are specialty use cases, right? This could be hospitality style access point where you have to mount the access point on the wall, you need additional Ethernet ports, you may have size or cosmetic restrictions. The APs, the higher end APs need more power, you may not have enough power, even though many of them have kind of reduced functionality modes. So just all things to think about when you're thinking about which AP to choose. And so, yeah, this was a topic that I thought needed a revisit just to see if the conclusions that were drawn before still apply. I think largely they do. That means the RF, the math hasn't changed, which is good. And so that's it. Thank you, everyone.